Yeah.
I'm not selling it, right? Hello and welcome back to Calculus1 on this wonderful Tuesday. No snow, which is right unusual. Oh no, snow is every Wednesday. Today is Tuesday, so we're good. Tomorrow. So the topic for today is graphing functions. We're going to graph functions by hand. Now, I'm not talking about x squared, because we all know dealing with x squared very quickly. I'm talking about ln squared of x plus 3, or something interesting like that. So we want to first, and I'm not going to teach any new concepts. We're going to take concepts from algebra, concepts from pre-calculus 1 and 2, and then what we learned in this class, and put all of that on the list of 13 things that we need to calculate before we draw the function by hand. It's very structured, and it's just a whole bunch of calculations in one spot. Hence, I said these questions are very good for killing time and developing carpal tunnel, right? Because each one of these is like 2 pages plus and stuff. Anyway, so what is the shopping list of things that we need, right? Calculations we need to do this. So we need, number 1, domain. Number 2, that we will pretty much always skip, range, because you technically see the range after you draw the function. Number 3, X-Intercept, and you get that when you set y equal to 0. Number 4, Y-Intercept, when you set x equal to 0. Number 5, vertical asymptote. Now, when it's obvious, and you can do it using, the basic methods from pre-calc 1, do it. But when it's not obvious, you have to do the limit. So I'm going to say pre-calc 1 or limit f of x as x goes to c plus or whatever to give you positive or negative infinity, because that was the way to find the vertical asymptote. 6, horizontal asymptote. Again, either you memorize the pre-calc 1 or limit x goes to either positive or negative infinity of f of x equals to L. Now, off of this branches the end behavior. So we can do that as well. 7 is the slant asymptote. And that one is only when you have the polynomial p of x divided by polynomial q of x. That's a bad way to write it that way. Hold on. Let's write a x to the p divided by b x to the q. And then we know that p is equal to q plus 1. So if you have polynomials where the degree on the top is by 1 bigger than the degree in the numerator and denominator, that's when we have the slant asymptote. So this is the first 7, and mainly this is your pre-calc and algebra. Then we are moving into calculus realm. We are going to do everything that we can do off of the first derivative. So first derivative. Now, what are the things that we get off of the first derivative? Well, first of all, we get critical points. Now, those critical points, we also have intervals of increase, decrease, which for free gives us min or a max. So these are all the things that we can figure out from there. Number 9, the second derivative, right, gives us A, inflection points. And then B, intervals of concave up, concave down. Number 10, you can also get the symmetry. Most people don't bother. Number 11, if needed, additional points. I'm going to put in parentheses over here, pick x. Right, you pick your x's. And then 12, graph. Bueno? So this is what I call a shopping list. And you go, right, down, shopping list. So what do I have first? Well, first we need a function. So, and great, I did not get the book going over here. Does anyone have a book by any chance? No? No. You have the book? Perfect, because the computer is going to take 15 minutes to start and then... Thank you. So now, what do I have? Linear approximation. That's next section 4, 3 graphing functions. So we are going to do 3 examples. We're going to do basic polynomial functions to learn basic stuff. Then we are going to spice it up into a rational function. And then we can do ELN, whatever you want. And that should be enough. So for this first example, we're going to go with one of the basic polynomial functions. How about 13 is good? Okay, good. So 13 has f of x is equal to x minus 6, x plus 6 squared. Oh, actually I need for more than that. All right, so what's happening here? Well, we're going to go down the list. Number 1, domain, polynomial. And we had the theorem in pre-calc 1 which said that the domain has to be negative infinity to positive infinity for all polynomials. That's the first thing. I said skip the range. So number 3, X-Intercept, set y equal to 0. So we have x minus 6 times x plus 6 squared equal to 0. Well, we use a zero product rule. Aren't we lucky over here? So x minus 6 equals 0, and x plus 6 equals 0. So x equals 6, and x equals negative 6, m2. What does that mean? That means that it's multiplicity 2. There are 2 roots there. Now, if you forgot what the multiplicity is, when you have a root that's multiplicity 1, the functions just shoot through it. When you have a root that is multiplicity 2, the function bounces off of it in a quadratic fashion. When you have multiplicity 3, then the function passes through in a cubic fashion. So all of these multiplicities depend on the exponents that you have when you have these factors. This is only for polynomials, obviously. So if you notice on the first one, the exponent on x minus 6 is 1. So I have a single root at x equals 6. So that's multiplicity 1. But then x equals negative 6 is multiplicity 2 because x plus 6 was squared. If I set each one of those parentheses, I would get negative 6. And then the second one will also give me negative 6. So I have 2 of those. So that's why it's M2. So now I have that. Now, wouldn't you agree that you already kind of see that there's going to be a minimum here or a maximum? Because you know that this multiplicity 2 has to bounce this way or bounce that way. So you already know that the min or a max needs to happen at this point, and you will be looking for it later. But, you know, for now, let's just keep it there. Simple. Number 4, Y-intercept, set all x's equal to 0. So you have 0 minus 6 times 0 plus 6 squared. This is negative 6 times 36, which is what? Very good. $216, right? So these are the points I have so far. I have 6, 0 as x-intercept, negative 6, 0 with multiplicity 2, and I have 0, negative 216. These are some of the points that are important so far. All right, number 5, number 6, number 7, no asymptotes for polynomials. That should be clear. No asymptotes of any kind for polynomials. And then we have number 8, which is the first derivative. Now, for the first derivative, in this case, you can do logarithmic, or you want to do product rules. It doesn't matter. We can do product rule. You have to find product. You have to find derivative. You have to have it in a factor form because you will be setting it equal to 0 for the first derivative test, right? So copy the first, x minus 6, times derivative of the second, which is 2 times x plus 6, plus copy the second, x plus 6 squared, times derivative of the first, which is 1. So now to factor this, you factor out x plus 6, and what's left is 2x minus 12 plus x plus 6 from the second one, for the total of x plus 6. And what is this? 3x minus 6. So your first derivative simplified, because you want to have that handy. We'll go back to it later, twice. You have x plus 6 times x minus 2 with the 3 factored in front. Now you want to set that equal to 0 to find your critical points. And clearly x equals minus 6 and x equals to 2 are critical numbers, which you plug back in original problem to find their y values. Now you already have the y value for negative 6 because that was one of the points, right? So you see the critical point at negative 6, 0, which you were expecting because multiplicity 2. Now x equals to 2 is going to give you f computed at 2, which is 2 minus 6, and then 2 plus 6 squared, which is negative 4 times 8 squared, which is negative 4 times 91. And when you multiply that, that's negative 364. So we have another critical point at 2. Oh, sorry, 64. I don't know. I'm supposed to say 64. 4 times 64. I don't know. I checked out. That's 256. I was just testing you, and you just passed. Very good. We are going to do partition. We know that goes from negative infinity to positive infinity, and we are partitioning in negative 6 and positive 2. The test value I'm picking, negative 7, 0, and 3. It doesn't matter what you pick. You can pick any values in these regions. And then you have to test these in the first derivative, because it's first derivative test. Now, we don't care of the actual values we compute. We just care about the sign. So when I do the first derivative of negative 7, that's going to be 3 times negative 7 plus 6 times negative 7 minus 2. All I see here is the positive times a negative times a negative, which is positive. Larger than 0 increase. I don't care what the numbers are. You can go and compute numbers. It's okay. But no one cares. The 3 is positive. Negative 7 plus 6. Yeah, I know it's negative 1, but I don't care. I know that the negative 7 is more negative than positive 6 is positive. So the combination of the two, right, is going to be negative number. And both negatives are going to give you negative. F prime at 0 is going to be 3, 0 plus 6, 0 minus 6. That means 0 minus 2. Congratulations. Which is, I switched it, I said, right? So that's a plus, and that's another plus, and that's a minus. So this is a minus. As you can see, I don't compute. I just know it's a positive times a negative. You can go and get your value. It's going to be negative 36. But we don't need actually that value. We just need to know it's negative so we can put decrease. And f prime at 3 is 3. 3 plus 6. 3 minus 2. And this is positive times positive times positive. When you multiply 3 positive numbers, you get positive. So it's increase. So what do we get for free? At negative 6 we have a max. And at 2 we have a min. Yay! Second derivative now. That was number 8, right? No, number 9. Now second derivative we have to get by looking at the first derivative. F double prime, we copy 3, see you next week. So copy the first, times derivative of the second, which is 1, plus copy the second, which is x minus 2, times derivative of the first, which is x plus 6. So all of this is 3 times, and now this is 2x plus 4. And you can kick 2 out, so it's 6x plus 2. So now I have my second derivative, which is 6x plus 2. Set that equal to 0 to find inflection. So 6 equals 0 has no solution, but x plus 2 equals 0. X equals negative 2. Plug that negative 2 in original function to find my y value. So that's negative 2 minus 6 times negative 2 plus 6 squared. That's negative 8 times 4 squared is 16. So 8 times 8 is 64, negative 128. So we have a point negative 2, negative 128 as our inflection point. Partitioning for the second derivative test. We are on the infinite domain, from negative infinity to positive infinity, and the only partition we have is at negative 2. So the test points, negative 3 and 0. Yeah, you can use negative 1, but 0 is much easier to compute. So let's use that. And now use second derivative at -3 is 6 -3 plus 2. That's -6, right? But, as I said, positive times negative is negative. Less than 0, concave down. Again, me not caring about the value, is just the sign. And then 6 of 0 plus 2, which is positive times positive. It's positive. So concave up. And I'm going to leave the rest, right? There's nothing else I need to compute. I can just pick all the values that I have and then go from there. Now, the issue with this graph, obviously, is that we have a lot of very negative points. So what's the most negative on y? Negative 256? Negative 256. Okay, so I'll have two different scales. A scale for x-axis is 2 units, so 1, 2, 3. -1, -2, -3. And then scale for this one is going to be in hundreds. So maybe -100, -200, -300. The goal is to put the points, all of the points in asymptotes first. So what are all of the points that we have? I'm going to go all the way on the top. Oh, I have all the 6s. I forgot about those. Okay. Let's move the graph and make it bigger. So what I'm going to do is I'm just going to extend this to include positive and -6. So 4, 5, 6, 7, -4, -5, -6. Good. What do I have? I have intercept at 6 and -6. I have the y-intercept at -216. Right there. That's -216. After that, I have critical points. Oh, -60 is a max. So -60 is a max, it gets a frown. Right? Because it has to be a max. And then I have a min at -256. 256. And that's a min. So it has a smiley on it. And then I have inflection point at -2, -128. And now I just need to connect these. If you stare enough at this, you will see that the function comes in from this end, goes through this, goes through this, goes through this, goes through this, and then goes through that. I just need to make it nice. But do you see that this is actually a cubic function? what was our original problem? It was x plus 6 times x minus 6 squared. So that's x cubed. If you multiply all of that, first x is not on any power, second x has a power of 2, so altogether you have 3 x's, right? So it's x cubed. We know that x cubed, I mean, this is terrible. I'm going to do a much better job now. But as a sketch, I know what to follow. I have to, and this is what the cube function looks like. So now I'm going to come in. I'm going to bend, pass through here, pass over here. So I need to have, like, I know now that I need to make a Y, right? So it changes concavity from being concave down to concave up. So it can curve nicely into this. This is why, you know, the preliminary drawing is just to connect points. And now I'm going to make much better picture and then erase this. So now I know that I need to go wide for the max, fall as a concave down here, and then bend it into concave up. And then as soon as I hit this one, go straight up through this point. There it is. Much better job on drawing the function. And then we can erase all of the little constructions that we needed. And you have your max, and you have your min, and you have your X-intercept, Y-intercept, and all of that. Now you can go and check your concavity and increase, decrease. It was increasing up until -6. Look at that, increasing up to -6. You can see it on the graph. Decreasing all the way to 2. That's decreasing all the way to 2. And then increase after that. Concave down up to -2. Concave down up to -2. Concave up after. And those are also visible clearly in the picture. So it's fairly straightforward. It's just there's a lot of it. A lot of calculations. And as I said, we are not learning anything new in this section. We are simply putting a lot of math, you know, so far together for one problem. We are going to the shopping list of things. Let's take a look at another example. This is going to be a rational function. So we have f of x equals to x squared plus 12 divided by 2x plus 1. It's a rational function, and we go through the entire spiel of things, right? First off, we need domain. If we have anything in denominator that makes a 0, has to be kicked out of the domain. And we do have that, because 2x plus 1 equals 0 gives us x equals -1/2. So what's the domain? It's from -infinity to -1/2, union -1/2 to infinity. We had to kick out a single point. Number 3, X-intercept. So number 3 as X-intercept is set y to 0. So we have x squared plus 12 divided by 2x plus 1 equals 0. And when you cross multiply, denominator dies. So all I have is x squared plus 12 equal to 0. Now what does that mean? Well, there's no solution. This factors over complex numbers. So no solution means no x-intercept. That's okay. Functions don't have to cross x-axis. It's fine. Number 4, y-intercept. You set all x is equal to 0. And that's what we have over here is y equals 0 squared plus 12 over 2 times 0 plus 1. And the whole thing is 12. So the y-intercept, we do have y-intercept, and the y-intercept is 0, 12. That's a point we are going to draw. That's cool. Number 4. Do we have a vertical asymptote? Where are your chapter 2 skills? Do we have a vertical asymptote?
No.
No. Or yes?
No.
How do we find vertical asymptotes?
I think it's 0.
Where?
Denominator.
0 in denominator. Seen it.
And the numerator.
So 0 in denominator. Well, we do have that. X equals negative 1/2. Does give you 0 in denominator. So that's our vertical asymptote. Great. Do we have horizontal asymptote? No. Degree of the numerator larger than degree of the denominator? No how. Do we have slant asymptote? Do we have slant asymptote?
No.
Do we have slant asymptote? Yes. The degree in the numerator is by 1 bigger than the degree of the denominator. So, long division. You can do synthetic, but we're lucky here that we don't have to write that it's linear, otherwise you wouldn't be able to. So what do I have? I have 2x plus 1 divided into x squared plus 0x plus 12. I put that placeholder there. So now 2 into x squared goes 1/2 x times. When you multiply it back, you get x squared plus 1/2 x. And then you're supposed to subtract this. So what you get is negative 1/2 x, and then you drop 12 down. 2x into 1/2 x goes negative 1/4 time. When you don't have to multiply back because you're already done. Slant asymptote, y equal 1/2 x minus 1/4. Another, this is intermediate algebra skill to divide polynomials. So there it is used here. So we do have a slant asymptote. That's the piece that we need. Number 7, after the asymptotes, first derivative test. So first derivative of our problem, well, we have to go with quotient rule over here. We have 2x plus 1 squared in denominator, 2x plus 1 here, times the derivative of the top, which is 2x, minus copy the top, which is x squared plus 12, times the derivative of 2x plus 1, which is just 2. Now you have to fix this. That's 4x squared plus 2x minus 2x squared minus 24. All divided by 2x plus 1 squared. Simplify. 4x squared minus 2x is 2x squared plus 2x minus 24 equal to, divided by 2x plus 1 squared. Now equal to 0. Actually, you know what, let me write it one more time. So f prime of x is, you can factor out 2, and you get x squared plus x minus 12 divided by 2x plus 1 squared. And this is your first derivative. Actually, I don't want to box it because we're not going to use it for graphing, but we will use it for other stuff. So now when we set this equal to 0, all we have to worry about is the numerator being equal to 0. And then that factors over x plus 4x minus 3. X equals negative 4 and x equals positive 3. So now we get to partition. Domain was negative infinity to positive infinity. And in the game, to partition here, we have to include all critical numbers and all asymptotes. So we have the asymptote at negative 1/2. So we have partition at negative 4. We have partition at negative 1/2 or positive 1/2. What was it? Negative 1/2. And we also have partition at 3. That's 4 regions, right? 4 partitions. So negative 5, negative 1, 0, which is between negative and positive number, and then 4. We do the first derivative test for all of these, and you know what? I'm going to use my analysis. Now look at my first derivative test. It's 2 times x squared plus x minus 12 divided by 2x plus 1 squared. Would you agree that this is already positive 2, times, I don't know, divided by a positive because it's squared? Would you all agree on that? What are the arguments for that? 2 is always positive. So it's always positive. Squared quantity is always positive. So that's that. The only thing that I don't know the sign is the polynomial x squared over there. And that sign is going to depend on our points. So that's the only thing I have to compute, right? Because these positives, they don't contribute to the sign change at all, so I can ignore it. It's the sign of this that determines the signs in increase-decrease. That's called analysis. You don't have to compute. You can compute, obviously. Go and compute if you want to. So I have f prime at negative 5. So all I need to compute is negative 5 squared plus negative 5 minus 12. That's 25 minus 17, and I know that's positive. I'm not even computing it. That's increase. F prime computed at negative 1. It's negative 1 squared minus 1 minus 12. This is 1 minus 13. That's negative. Decrease. Aha! I know there is a max over here for negative 4. Beautiful. F prime computed at 0. Well, that's 0 plus 0 minus 12. That's negative 12. That's less than 0. That's another decrease. And finally, f prime at 4 is just going to be 4 squared plus 4 minus 12. And that's 16, that's 20 minus 12, which is more than 0, it's increase. So what we get for free is that this is a min. Oh, I didn't compute the y values for these bad boys. Okay. So y is equal to f of negative 4. So go back to original equation. Right, to calculate y's, you always have to go back to original equation. So f of negative 4 is 16 plus 12 is 28. Divided by negative 7 is negative 4. So I have the max at negative 4, negative 4. The other one is clearly 3, but let's compute that. So f of 3 is 3 squared plus 12 divided by 3 times 3 plus 1. 9, that's 20, divided by, oh, that's 10, so it's 2. So we have 3, 2. 3, 2 for a minimum, and 4, negative 4 for a max. Three squared is 9, 9 plus 12, oh wait, 9 plus 12 is 21. Rip. Oh, and this is 2 times 3. 2 times, I knew it that I computed the first time right. It's 3. It's 7. So it's 3. There we go. It's 3. Sometimes when it's obvious, you just know, and then I start doing it slow, and then I mess it up. Okay. Second derivative test, right? We have our increase-decrease. It's number 9. Didn't I mention killing time and carpal tunnel? The homework for this is going to be very interesting, depending on the definition of the word interesting, right? Tears? I mean, you can't point out a hard concept in here. It's just a lot of it. What happened? What happened? With the class?
No, I just said it's hard.
How about we take second derivative now? See what's going on. We have the first derivative here, so we copy this 2. 2x plus 1 to the 4th now, because you have to square it. Copy 2x plus 1 squared as is. Derivative on top is 2x plus 1. Minus copy the top, which is x squared plus x minus 12. Times derivative of the bottom, which is 4. 2x plus 1 cubed times the derivative of the inside. Nice. Isn't this cool? Anyone? Whatever. So 2x plus 1 cubed, 2x plus 1, I can kick that out. So 2 times 2x 1 cubed. And what's left? From the first one is left 1 minus, that's all gone, that's 8x squared minus 8x plus 8 times 12 is 96, right? Divided by 2x plus 1 to the 4th. But then these guys cancel. And just have 2x plus 1 there. So your second derivative is, when you combine everything, 2 times, and over here we have negative 8x squared minus 8x plus 95, no, plus 97 over 2x plus 1. So copy this one, the derivative of the 2x plus 1, copy this one times the derivative. Oh, that's where the mistake is. Guys, I'm taking the derivative of 2x plus 1 squared, not to the 4th. So this over here is 2. And that exponent doesn't exist. Okay, so just this is wrong, everything else is good. I didn't like it. Alright, so what can I kick out? I can kick out only one of these 2x plus 1s. And what's left is when I square this one, I get 4x squared plus 4x plus 1 minus, this is out, 4x squared minus 4x, and then minus, and the minus gives me a plus 48. 2x plus 1 to the 4th. Now these cancel, we get a 3 over here. Where's my spray? So now we have 2 in front. These guys drop. These guys drop. And all you have is negative 40, no, positive 49. So 49 divided by 2x plus 1 cubed. So the second derivative is, that's a 98, right? Divided by 2x plus 1 cubed. And that's my second derivative. Now 98 is always positive. This is cubed, which means it will be preserving the sign of the inside. When I set this equal to 0, denominator dies. You get 98 equals 0, which is not true. So no inflection point, because there's no solution to the equation. So when I do my partitioning, I only get to partition where? Since there are no inflections. Where do I partition? No. Why? It's a vertical asymptote, exactly. So you do partition over all inflection points and over all asymptotes. The only asymptote we have is negative 1/2. I mean vertical asymptote we have is negative 1/2, and there are no inflection points, so that's that. Pick negative 1 and 0 as 2 test points and do your second derivative test. So it's going to be 98 divided by 2 times negative 1 plus 1 cubed. That's 98 divided by negative 1. So that's less than 0. So it's a concave down. This next one is with 0. So it's 98 times 0 plus 1 cubed, which is 98 over 1, which is larger than 0, concave up. So yay! I have everything I need to draw this graph. What is the highest point and the lowest point? We have a negative 4, we have 12. Okay? So $13, $12. Okay, so this is it. All right, so what are my points? No X-intercepts, 0, 12, negative 1/2 on the asymptote. So 0, 12 is the over here. And now I have all of my points on the opposite side, so I'm just going to fix that. I'm just going to move these values to the other side. There we go. So I just make, because I need a negative 1/2 asymptote, and that's right here. So the red dashed vertical line is the vertical asymptote at x equals -1/2. Now what else do I have? I have -4, -4 as a max. And then I have 3 and 3 as a min. Right? Seems that the max is lower than the min. Let's check that. So -4, -4, 1, 2, 3, 4, 1, 2, 3, 4. So -4, -4 is here, and they want that to be a max. And then 3, 3, which is here, they want that to be a min. Well, that makes no sense, right? Which actually it does, because there's an asymptote in between them. You see that this one is going to drop from the top, pass through the Y-intercept, connect here, and shoot off this way. So it makes sense, actually. So when the asymptotes are out there, you can technically do whatever. So that's that. But we didn't draw the asymptote, the slant asymptote yet. So what's the slant asymptote? Slant asymptote has the function 1/2 x minus 1/4. So minus 1/4, that's 1/4, minus 1/4. And then you go 1 unit up, 2 units over. So 1 unit up is going to be 1/4 below 1. And then 2 units over. 1 unit up, 2 units over. 1 unit up, 2 units over. And then we connect this, creating the slant asymptote SA y equals 1/2 x minus 1/4. Now we have everything we need to draw our function. On the right hand side, the function is going to drop down through the Y-intercept, hit the point minimum 3, 3, and then bounce off to follow the asymptote. On the other side, it's going to come in, bounce off, and bend to follow the asymptote. This is -4, -4 max, and this is 3, 3 min. And there's your function. You can do it by hand. The problem is that it has about 20-minute calculation before that, but it matches everything. Don't you have concave down before the vertical asymptote? Yeah, you do. Concave down before the vertical asymptote. Concave up after the vertical asymptote. There's your concave up, right? So everything works. It's great. So this is how you kill time, right? It's excellent when someone, in the heated argument goes, what do you know? Let's graph a function. Let me show you. And then you bore them to death with a 45-minute calculation. And you say, here's a function. What do you know? So let's do the review. And then we'll do 2 more examples of this after the exam. Right? We need to do something with ln or e or, more interesting stuff than the only function, polynomials. we have square root. How about the square root of ln x squared? Right? Cool. Can do that. So let's switch gears, restart the stream for the review.